Good afternoon, everyone. I'm Shruti Chaman, and today I'll discuss the findings of research paper Deep Learning Based Real-Time Building Occupancy Detection using AMI data. I have provided the citation and link to the paper on slide 2 for your reference. Let's quickly understand the work done by authors. The paper presents a novel method to determine the presence of people inside the building using publicly available dataset, which is AMI data. It stands for Advanced Metering Infrastructure Data. The proposed method is a deep learning technique which combines the functionalities of CNN and LSTM for feature extraction from spatial and temporal data. The CNN simply has convolution and max pooling layers, and the bidirectional LSTM contains 3 hidden layers. Presented method achieves around 90% accuracy for occupancy detection. AMI might be a new term for you. Let me tell you some interesting facts about the dataset. It refers to an integrated system of smart meters, communication networks, and data management system. So how is this data useful for us? Smart meters measure and record electricity usage data at hourly intervals or more frequently. ECO dataset is a publicly available AMI data. It was gathered from 6 Swiss households over 8 months period. The data contains values of currents, voltages, and phase shifts. The occupancy is measured by manual labeling and passive IR sensors. Authors have divided the data into 60% training, 20% validation, and 20% testing subset for the experiments. We should understand the previous work done for occupancy detection. It can be done using intrusive or non-intrusive sensors. Intrusive sensors measure indoor environments, whereas non-intrusive sensors are basically infrastructure sensors, such as Wi-Fi, Bluetooth, RFID. Though the intrusive sensors give over 99% accuracies, they have very high installation cost. On the other hand, Wi-Fi gives 72.7% accuracy and RFID gives 88% accuracy. Thus, the limitations of both types of sensors can be overcome using AMI data. Previous work has been done using non-parametric modeling, ensemble learning, and shallow learning. It gave accuracies in the range of 80 to 90%. Thus, in this paper, authors have compared the performance of proposed deep learning approach with other traditional machine learning techniques. On this slide, we see a big block diagram of the proposed architecture. Don't worry, it's not that difficult to understand. I have highlighted the different blocks for you. The red box represents the input AMI data. In our case, these are the occupancy measurements. So this is a binary classification problem. In simple words, we just need to find if the person is present or absent. In technical terms, the output will be just a 0 or 1. The green box shows the CNN part, made up of 2 groups of convolution and max pooling layer. The ReLU activation is applied to the output of convolutional layer. It introduces the nonlinearity in the network. ReLU is advantageous in terms of computational efficiency, convergence, and the performance. Blue box borders the bidirectional LSTM, long short-term memory. CNN can only extract these spatial features. In order to understand the dependencies of these features, or we can call it as a temporal feature extraction, we use this bidirectional LSTM. The formulas representing this entire model are listed on the next slide, which will help you to understand the maths behind this architecture. BiLSTM learns the contextual dependencies is forward and backward direction. Purple box shows the last part of the architecture, which is made up of 2 fully connected layers followed by a sigmoid function. As this is a binary classification, sigmoid is a classical solution. Let's understand the maths behind the block diagram. We take input AMI data represented by X. It has n data points with f number of features. So the vector dimension is n by f. The output simply 0 or 1 represented by y, so it has length n. Ultimate model function f of x W is nothing but LSTM function applied on output of CNN, that is FLSTM on FCNN. X refers to input and W refers to the learned weights. Loss function is weighted binary cross entropy, where small w is binary cross entropy weight. Loss function will optimize the learned parameters. The last two formulas represent the operation performed by the bidirectional LSTM, where H is the hidden state, F is the forget gate of the LSTM, which simply measures in both directions using past and future hidden states. This huge architecture obviously needed best hyperparameters for the best performance. Authors followed the grid search optimization with tenfold cross-validation to find the best hyperparameters for all the layers. 20% of the neurons are dropped out for the highlighted layers. Dropout clearly eliminates the randomly selected neurons. This helps in avoiding overfitting. The results of the experiment are shown using 2x2 confusion matrices for CNN by LSTM, KNN, SVM, GP, random forest, and MLP. All the algorithms are tested using Keras and Scikit library. The training is performed on NVIDIA Titan V GPU. Confusion matrix gives us the true positive, false negative, and true negative values. With these values, we can calculate accuracy, sensitivity, specificity, precision, and F1 score. The red box on the left figure shows us that the CNN by LSTM model is more accurate than other benchmark models for all four cases. The different cases are just taking the random datasets for experiments. The calculated metrics are shown on the right figure. The result for case 1 are clipped, and we can see the highest accuracy and F1 score is obtained for the proposed method of CNN by LSTM. The issues faced by authors during the experiment can be overcome with some future implementations. I have listed the issues and proposed solutions. First, there was irregularity in the results of 4 cases. This was due to the imbalanced division of data used for training the model. Thus, in future, we can make sure the division of the dataset is fair. Second, in real world, we don't get the labeled AMI data. So we can check or test the unsupervised machine learning algorithms for occupancy detection. Third, we can gather more diverse data in terms of demographic areas. And at last, we can also try deep learning with attention mechanism for occupancy detection. I hope I explained the paper in a simple way. Please feel free to ask any question related to this paper. Thank you.